my name is Henning, and this is a video journal on the experiment of the synthesis of lidocaine, which is a local anesthetic. Before I explain the experiment further, let me break it down into the 3 separate weeks and parts that we did it in. In the first week of the lidocaine experiment, we worked on the first step of the 2-step synthesis of lidocaine, which is the acylation of 2,6-dimethylaniline with chloroacetyl chloride. Week 2, we did the second part of the reaction, where we did the SN2 substitution of N2,6-dimethylphenyl chloroacetamide with diethylamine. Lastly, in week 3, we take the crude lidocaine freebase that we received in week 2 and purified it through a process that we call recrystallization. The purpose of this whole experiment is to start with diethylaniline and through a series of reactions to make lidocaine. To give a little brief background of lidocaine, lidocaine is an important anesthetic that was created during World War II. When injected into tissues, like our gums during dental work, which I just got done a few weeks ago with a very painful cavity filling, lidocaine numbs the injected area and lasts anywhere from half an hour to 3 hours. Lidocaine is also used in aloe vera gel to ease the pain of sunburns. In a physically solid state, lidocaine is a white crystal. The theory behind this yield is done through a series of mechanisms. The mechanism starts with the production of 2-chloral N2,6-dimethylphenyl acetamide and byproduct HCl through acylation, making a new amide functional group from the starting material. First, the lone pair from the amine on the 2,6-dimethylaniline, which is the limiting reagent, attacks the electrophilic carbon of the carbonyl group on the 2-chloroacetyl chloride to form the quaternary intermediate. Next, the elimination of chloride through the satisfaction of the carbon-oxygen bond gives a protonated secondary amide intermediate along with the chloride ion, which goes back and deprotonates the secondary amide, leaving us with the product in week 1, which is the chloroacetamide. The next step of the mechanism is the SN2 backside substitution reaction, where the nucleophilic and basic second-degree amine lone pair electrons from the diethylamine attack the electrophilic carbon, which is connected to the chlorine on the chloroacetamide, which puts it in the transition state in which the diethylamine and the chloride are opposite to each other to give lidocaine hydrochloride salt, which is a 3rd-degree ammonium salt. Next, diethylamine, which is in excess, acts as a base, and its lone pairs attack the nitrogen on the lidocaine hydrochloride. This acid-base reaction, involving a hydrogen ion transfer, then creates lidocaine mixed with diethyl ammonium chloride. The week 2 experiment ends with the liquid-liquid extraction using HCl followed by freebase with potassium hydroxide, producing lidocaine freebase, which is water insoluble. This second step creates a new 3' amine. Week 3 uses recrystallization using pentane in order to achieve a more pure version of lidocaine freebase because our lidocaine from the SN2 reaction is a very crude synthesis. The IR spectrum of chloroacetamide is enough to explore both the IR of chloroacetamide and lidocaine because they are very similar in the functional groups that are active on the spectra. IR is described as an analytical method that provides useful information respecting the functional groups of a compound. The functional groups of chloroacetamide that will give positive signals through IR are the secondary amide, the sp2CH phenyl ring, the sp3 alkyl group, and the C double bond O of amide. 3,212 centimeters to -1 is the NH bond of secondary amide. 3041 is sp2CH bond of the phenyl ring. 2857, 2924, 2972 are the sp3CH of the alkyl group, and finally the 1642 is the C double bond O of amide. Thank you so much for listening to my video journal.